This is Science Friday. I'm Ira Plato. Who among us doesn't stop and marvel at a rainbow? It is really a wonder of nature. And if you don't believe me, just ask the double rainbow guy.
Whoa, that's a full rainbow. All the way. Double rainbow. Oh my god. It's a double rainbow all the way. Whoa! Oh my god! Oh my god! Oh, oh my god! Woo!
Whoa, a lot of enthusiasm there. And the double rainbow is just the beginning. Did you know there are moon bows at night? And yes, there are even white rainbows. And how about this? Each of us has our own rainbow. The one I'm looking at is different than a rainbow you're looking at standing next to me. We'll get into all of that, the science, the magic behind these majestic multicolored arc forms. My next guest is here to be our rainbow connection. Get it? And to tell us all about rainbows and why Hawaii might be the rainbow capital of the world. And there's an app that will let you become a rainbow hunter if you'd like. Let me bring on a man who had a double rainbow for breakfast, he tells me. Steve Businger, professor of atmospheric sciences at the University of Hawaii in Manoa. Welcome to Science Friday.
Thank you, Ira. I'm thrilled to be here. I'm a big fan of your show.
Thank you. Nice to have you. Just a quick note to our listeners, our segment is being recorded with a live Zoom audience, and you all can learn more about joining a future live recording at sciencefriday.com/live stream. We want to hear your rainbow questions, so let us know in the Zoom chat. Was I right, Steve? You had a double rainbow for breakfast?
Amazingly, I woke up this morning, looked out the window, and there was a spectacular double rainbow right outside my window. So I quickly went outside with my camera, took some photographs, uh, and it was amazing. Yeah.
Yeah, we have all kinds of rainbows up on our website, and maybe even Steve's is up there, so you can go check it out. I think it's great that you had a double rainbow for breakfast because I love rainbows. They are works of nature, but they're also works of physics, right? Tell us how a rainbow works. Where did the colors come from? How does all of this happen?
Well, you need sunshine and you need some rain, and that's the combination which we get a lot in Hawaii. Uh, the sunshine, it goes into the raindrop. It refracts as it goes in. It reflects off the back of the drop, and it refracts again as it comes out. And it in the process, the light from the raindrop has an angle of 42 degrees from the incoming sunlight, and that is the angle of the rainbow. And it is this refraction that is different for different colors or wavelengths of light that separates out in the process to produce this gorgeous rainbow.
And so things have to be very specific. You have to get that 42-degree angle, right? You have to have the sun behind you then.
That's right. You have to have the sun behind you. And if you look at the shadow of your head when you're standing looking away from the sun, the shadow of your head, that's the point where you measure the 42 degrees from. And the funny thing is, the guy, your friend who's standing next to you, um, the shadow of his head is the center of his rainbow. And that's why no two people see exactly the same rainbow, because each rainbow comes out from the shadow of your head at 42 degrees.
So the raindrops that are falling down as they're making the rainbow are different for me than they are for you. That's what you're saying.
Right. That the colors are coming from a different set of droplets. And
Wow.
therefore, it's two different rainbows, essentially.
That really is cool. So if the rain droplets are falling, we get that Roy G. Biv sort of color, right?
That's right. It's an interesting thing because Descartes, back in the 1600s, he was the first one to actually follow the path of the light in the raindrop and have it come out. But he didn't explain the colors. It was um, Sir Isaac Newton who explained the dispersion of the colors and actually came up with spectrum, that word. And he decided that there were 7 colors in a rainbow. And it turns out that the 7 colors is a bit arbitrary, but it does follow along with the 7 days of the week and the 7 main major planets and the 7 musical notes in an octave. So he felt that that was really compelling, that there ought to be 7 colors. But the human eye can see many, many more colors than 7.
Let's talk about the ingredients for a rainbow. What are the environmental conditions that you need for a rainbow to form and for anyone to see it?
Right. It's interesting because a place like Seattle or London gets lots and lots of rain, but they don't get as many rainbows as Hawaii. And the reason is that you need to have rain falling out of relatively isolated showers with lots of ability for the sunshine to get in on the side. And another thing that we have in Hawaii, plus the fact that we have these isolated showers, trade wind showers that are called, is that we have mountains, and the mountains enhance those showers and cause there to be, as the air comes down on the lee side, it causes the cloud to evaporate and have sunshine. So in the town of Honolulu, which is on the lee side, you look back towards the mountains in the afternoon, and there are lots and lots of these showers creating rainbows.
Let's get into this double rainbow question. We started out the segment on double rainbows. Let's go to our first listener question. Barry has a question about the rarity of double rainbows.
Yes, actually, my wife Audrey was asking it. It's just double rainbows. How common are they? And can you have rainbows that are triple or even more than that?
Oh, yeah, good question. What do you say, Steve?
That's an excellent question. It turns out that the double rainbow is the product of 2 reflections at the back of the drop. So that the primary rainbow has 1 reflection, and the double rainbow has 2 reflections, and it comes out at 51 degrees instead of 42 degrees. So it's a little higher above the primary bow. And because there's an extra reflection, the colors are reversed with red on the bottom and indigo on top. There are possibilities for more internal reflections, and therefore there is the 3rd rainbow and the 4th rainbow and a 5th rainbow, etc. But with each reflection, you're losing a bit of light out the back of the drop. And so it's very rare to be able to see these other rainbows. The 3rd rainbow creates a big circle around the sun. And then the 4th rainbow goes back in on the other side. And in the last few years, it turns out with all these digital cameras and people taking photographs, that there actually have been some photographs, some photographic evidence of these tertiary and quaternary rainbows. It's really fascinating.
So to separate the different rainbows, the multiple rainbows, there's a dark band between the rainbows, right?
Yeah, and that is because as the light comes into the raindrop, if it comes at the right angle to produce a rainbow, which is 42 degrees, then it's bright at that spot. But if you go a little bit higher, it turns out that the light again goes less than 42 degrees. And so above 42 degrees, there's an area where the light can't easily get out of the drop. And similarly for the double rainbow with the 2 reflections, the light can't seem to get underneath the 51 degrees. So between 42 and 51 degrees, there's an area where very little light is actually able to get out and come back to your eye. And it creates this darker band.
Fascinating. Let's go to Sophie, who has a question about a specific kind of rainbow. Hi, Sophie. You're next. Okay, I think I know what Sophie was going to ask him. If she's around, she can ask it later. She wanted to know what causes solar glories, the circular rainbows you can sometimes see from a plane. I've heard something about quantum tunneling, but I have no idea what that means.
That's a wonderful question, Sophie. Yes, a glory is something that you see when you're in a plane or a helicopter and you're looking away from the sun. And it turns out that it's in a cloud, not necessarily caused by rain, but instead it's caused by cloud droplets. And these droplets are pretty uniform in size. And there's an interference pattern that happens due to the scattering. It's called Mie scattering. When the light wave is about this, a little bit smaller than the droplet, the cloud droplets, then you get this very, very active Mie scattering, and you get an interference pattern. And it's kind of like looking at the rainbow pattern on a CD, where the light comes in and it interferes when it comes back out, and the interference separates the colors because the colors have different wavelengths.
So the rainbow actually forms a whole circle instead of being cut off on the ends.
That's right. It's a whole circle, and it's pretty close around the shadow of the observer. And a similar thing happens when you look at the sun. You got to be careful, though, you don't blind yourself. But if you have a high cloud that is thin and is made of uniform cloud droplets, it'll form something called a corona, which is a rainbow color around and close to the sun or the moon.
Wow, there's so many things about rainbows that are fascinating. For example, I hear that you can have rainbows that are a single color. Is that right? How does that happen?
Well, let's say that there's just a little bit of volcanic emission that happens in Hawaii. We get a little bit of foggy aerosols in the air that scatter the blue light and the green light out. And so what's left is this reddish orange light. And when that hits the rain, it produces a red rainbow. Now, on the other side, there is a possibility to get a white rainbow too. And we call that a cloud bow or a fog bow, depending on what the cloud is that's producing it. So in that case, you have the droplets are small enough so that there's enough Mie scattering going on, and there's a blurring of the colors. And since they all kind of blur together, they become white light again, and that gives you a white rainbow. And the interesting thing is that the Hawaiians had a saying that if you saw a white rainbow, it was good luck. It meant prosperity.
And rainbows are sort of sacred in Hawaii, are they not?
They are considered a path between our plane, the Earth, and higher dimensions. And other cultures have a similar feeling that the rainbow represents a link between Earth and heaven.
That's quite interesting. And rainbows at night, do we have a special name for them?
Well, moonbows, of course.
Moonbows.
Yes. And the moonbow is more restricted because we don't always have a full moon. And you need a lot of light from the moon in order to create a moonbow. The human eye is less able to see color when the light is very dim. Think about a car driving by at night. It may be red, but it kind of looks black. So the moonbow has less distinct colors than the rainbow does. However, digital cameras now can create some beautiful photographs of moonbows. So it's definitely worth going out and looking.
Now, I understand that you have a study that makes the case that Hawaii is the rainbow capital. Tell me, what conditions make Hawaii the capital for rainbows?
Well, we are the rainbow state after all, and our sports teams are called the Rainbow Warriors. There's lots of cultural examples of rainbows, and a lot of the businesses here have rainbow in the name or rainbows on the side of the buildings.
And I'm sorry. Go ahead.
Well, so that's just kind of a local backdrop, but it turns out that there are lots of reasons why Hawaii is special when it comes to rainbows. Um, I've already talked about some of them. The trade winds blow 7 days out of 10 and bring these isolated showers, which are very perfect for rainbows. The mountains produce updrafts on one side and sinking motion on the other. So you get rain over the mountains and clear skies in the lee. Another great opportunity for rainbows. Then we have very clean, clear air here. Most of the time, we're very far from any pollution sources, from dust and pollen that you might have on the mainland. And so the air is pretty clean, and that results in very strong sunshine that produces a brilliant rainbow. Now, the last thing, which is related to all that, is that the clouds here, because the air is so clean, have fewer cloud droplets. And what that means is that the moisture in the air is going to be divided over fewer individual droplets. And this makes the clouds more efficient at producing coalescence, where the rain comes together and produces rain droplets out of relatively shallow, small clouds. And so we have lots and lots of this rain coming out of small, shallow clouds with bright sunshine coming in.
I
So
love
it's
these.
a combination.
I love these details. Who knew? This is rainbow geek heaven that you're talking
It is
about.
indeed.
We talked to Puakea Nogelmeyer, who studies Hawaiian language, and you worked with, and he talked about how Native Hawaiians describe rainbows.
There's a really high level of specificity in Hawaiian. In English, I think we use rainbow a great deal. There's a rainbow over the ocean, there's a rainbow there, where Hawaiian would distinguish that more and say it's a pillar of color, it's a band of, so it's a different kind of specificity, I think, is all. Also, the notion of Roy G. Biv, that's sort of culturally defined. Those distinctions of color are sort of uniquely English, yeah. Blue, indigo, and violet actually merge into a single sort of uliuli in Hawaiian. Anuenue is the baseline of the arc of color. It has as much to do with intensity as with color distinction.
And he had this to say about these observations as science.
It kind of overlaps almost in the sense of citizen science, right? Mm-hmm. I mean, isn't science just sort of observation that's verified over, repetition and collection of data? And so Stephen very much saw that the reports, because mostly we work with Hawaiian language newspapers, and because they were throughout the archipelago, anything that happened would be reported, whether it was from Kauai or from Hawaii Island or Maui. So the comparison of reports, Stephen found just invaluable in the notion of, this is science data, whether it's scientifically approached or simply as an observer approach, it's invaluable stuff.
Yeah, Steve, how did you work with all that scientific citizen science data?
It's interesting how observant the Hawaiians were, much more so than we are. We're kind of glued to our computer screens and our iPhones, and the ancient Hawaiians were keen observers of the natural environment, and their survival really depended upon that kind of very careful observation. They had names for winds coming down different valleys and from different directions. So they have hundreds of names for different winds. They have many, many names for rainbows. I mean, I just went to the dictionary and pulled out 20 names, but it turns out there are many, many more. And from these citizen science articles that were published in the newspapers, we discovered that there was a Category 4 hurricane that hit the Big Island and Maui in 1871, and we could see exactly what the track was, and we knew what the damage was by the descriptions of what happened to the trees and so forth. And it made a difference in how we think of hurricane risk in the Hawaiian Islands. So these citizen science observations have real modern day implications.
That's amazing. That's really cool. Let's go to a next question from listener Renoir has a question about rainbows on other planets. Yeah, I'd like to know that. Go ahead.
Yeah, I just had a question about how a rainbow might look on another planet. Depending, I guess you wouldn't really know because we haven't really seen one, I don't think. But I was curious about how the sun, various suns, okay, and their wavelength frequencies might affect how a rainbow would look. And also, do you need water droplets, or could you have other chemicals or whatever in the atmosphere that would create a different type of rainbow? Thanks.
Great question. What do you say to that, Steve?
Oh, that's a wonderfully inventive question, and it shows a lot of creativity. I haven't really thought about that, so this is just off the cuff. Certainly, if the sun or the star that this other world is orbiting around has a different color than our sun, then, and it also depends on the eyes, how they have developed in the life form of this other planet. Of course, if we travel there, then it would be our eyes. But yeah, there certainly could be other kinds of precipitation and the different refractive index associated with that. One could imagine, maybe do a little bit of research on this to make a case for a different look of a rainbow on a foreign world. I think it's really intriguing.
Yeah. So if it's raining nitrogen or something, it's going to look a whole lot different, or methane or whatever it is. Let's move it back to Earth for a bit, because I'd like to know if a rainbow that is formed in Hawaii would look different than, say, a rainbow in Colorado.
Well, yeah, that's a good question. And the answer is it very well could look quite different, because in Colorado, what you have is a situation where there's lots and lots of aerosols, pollen and dust and little pollution and whatnot in the air. So you have many, many small cloud droplets. And those cloud droplets, because they're so small, they're not going to form the kind of rain that we have in Hawaii. They're going to go up above the freezing level where ice crystals are formed. And the ice crystals are going to grow at the expense of the droplets, and they're going to form the rain. That's called a cold rain process, which happens on the mainland. And the cold rain process has a different cloud size, drop size distribution. And so the rainbow is going to look different. It might be a little broader than the rainbow because of the more different sizes, so it's not as focused. And there is even the possibility that you would have a rainbow from the one cloud in the front with fine droplets, and then behind it and have a different cloud drop distribution, and that you would actually see two different rainbows because of the difference in the cloud drop distribution. It gets wild and crazy out there.
That's how we like it. So rainbows then can tell you something about the atmospheric conditions in which they're forming.
Yeah, that's a very insightful point, Ira, and maybe I should write an NSF proposal to look at what can rainbows tell us about the microphysics of clouds.
Okay, well, we'll be right with you on that one. I know that you're also studying how climate change might affect rainbows. What have you found about that?
Well, that's a paper which I'm not the lead author on, so I don't want to say too much about it. But it is an intriguing idea that as the climate changes, the nature of the precipitation coming out of the clouds, or the nature of the clouds producing the precipitation, is going to change. And the early results are that there will be more of these isolated type convective showers further north. Whereas now it's mostly stratiform big cloud shields that don't allow for rainbows. Certainly, if the climate gets drier, you're not going to get as many rainbows. So It's that change in the nature of the clouds, and it's a change in how much rain you have that will change the distribution of rainbows. And it's a really fun, intriguing study. And when it comes out, maybe you'll invite me back.
You've got a standing invitation. And we're running out of time, but I want to get to something I've been dying to talk to you about. I know you're creating an app called Rainbow Chase to help people track where a rainbow might be. It sounds to me like tornado tracking, but you're doing it with rainbows, finding a rainbow forming.
Yeah, you know, a friend of mine, Paul Sin, he's absolutely nuts about rainbows. He's actually originally from South Korea. And in Korea, when they see a rainbow, it makes the nightly news. And so he and I dreamed up this idea of photographing a circle rainbow from a helicopter. And we needed to know where to go with the helicopter. So I said to myself, well, why don't we create an app for a smartphone where we can give the helicopter pilot some guidance as to where he should fly to get the circle rainbow. And that's sort of described in this paper that I published. But the Rainbow app is actually available. You can download it. You just type in Rainbow Chase and you can download it for free, and it will remain free because our goal is to bring more rainbows into people's lives. And unfortunately, at the moment, it's only only available in Hawaii in terms of the. So if you download it, you'll see Hawaii, and you can look at where the rainbows are in Hawaii. But we are planning to expand it to the mainland, and that's our goal.
So if you want that rainbow connection on your app, you've got to go to Hawaii to use it.
That's right, for now, but in the future.
All right, I'm looking forward to that, and I'm very happy that you took time to talk with us about rainbows today, Steve.
Well, it's certainly a pleasure of mine, Ira. It's been a lot of fun.
Dr. Stephen Businger is professor of atmospheric sciences at the University of Hawaii in Manoa. And if you want to see photos of these double rainbows, the 360 bows, and more, you can get your rainbow fill at our website at sciencefriday.com/rainbows. And if you want to learn more about joining a future live recording like we're doing now, go to our website, sciencefriday.com/livestream. That's about all the time we have for this hour. If you missed any part of the program or you'd like to hear it again, subscribe to our podcasts or ask your smart speaker to play Science Friday. And of course, we're active all week on social media, Facebook, Twitter, Instagram, or you can email us, scifry@sciencefriday.com. I'm Ira Flato. We'll see you next week.